The purpose of this presentation is to provide the viewer with a basic understanding of electrostatic precipitation methods used to control air pollution and control devices under this category. We will cover how do electrostatic precipitators, or ESPs, work, three types of ESPs and their design and components, proper operating conditions which include the voltage, current, sparking rate, and wrapping cycle, causes of decreased performance, performance monitoring. Electrostatic precipitators, or ESPs, remove particles from a gas stream by charging them either positively or negatively and causing them to be deposited on grounded collection plates. The collected particles may be removed from the plates as dry material, or they may be washed from the plates with water. Liquid particles are sometimes removed by simply allowing them to drain from the plates. Electrostatic precipitators are capable of collection efficiencies greater than 99%. There are three common types of electrostatic precipitators: dry negative corona, wet negative corona, and wet positive corona. The dry negative corona ESP is the most common type. As the gas stream enters the precipitator, its velocity is reduced as it passes through an expanding transition section. Several perforated plates are typically mounted in this section to help maintain proper flow distribution. Those plates located near the discharge of the transition tend to collect particles on their surface and must be cleaned periodically. The gas stream exiting the transition section flows horizontally through a large number of parallel gas passages, with vertical discharge electrodes mounted in the center and vertical grounded collection plates on either side. In most ESPs, small diameter wires serve as the discharge electrodes. In other designs, rigid mass or wires in rigid frames are used. The discharge electrodes are divided into fields. These are portions of the precipitator energized by a single transformer rectifier or TR set power supply. Most ESPs have 3 or 4 fields in series. However, very large units may have as many as 14 fields in series. A high negative DC voltage is applied to the discharge electrodes, creating a high-velocity electron discharge termed a corona. In the portion of the corona nearest the electrode, the impact of the high-velocity electrons with gas molecules produces positive gas ions and additional high-velocity electron charges. The positive gas ions attach to a small number of particles near the electrode, charging them positively. These positively charged particles deposit on the negative discharge electrodes, requiring the electrodes to be cleaned periodically. A short distance away from the electrode, the velocity of the electron charges reduces to the point where they begin to attach to gas molecules, charging them negatively. The negative gas ions attach to the remaining particles present in the gas stream, charging them negatively. The negatively charged particles then move to the collection plates and deposit on the surface. The particle property that controls the deposition and removal of particles from the collection plates is the particle resistivity. Resistivity is the opposite of conductivity. The desirable situation is to have particles that conduct away some of their charge once they reach the plate, so that the deposition of other particles is not inhibited, but retain enough of their charge to lightly hold them to the plate. This characteristic is termed moderate resistivity. If the particles have very high resistivity, they are slow to conduct away their charge, causing a negative charge to build up on the plates that inhibits other particles from depositing. Also, because of the high charge difference, the particles are tightly held to the plate, making removal difficult. If the particles have very low resistivity, they rapidly lose their charge when reaching the plate and pick up the charge of the plate, causing them to be repelled back into the gas stream, where they are recharged negatively. This process repeats itself until the particles exit the precipitator uncollected. Particles with very low resistivity, such as those with high carbon content, are not good candidates for dry electrostatic precipitation. However, many particles collected in ESPs have high resistivity. Examples include fly ash from combustion sources and cement dust. The resistivity of these particles is brought into the moderate range by a process known as particle conditioning. When the gas stream is below about 350 degrees Fahrenheit, adding moisture to the gas stream or reducing the temperature lowers particle resistivity. Resistivity can also be lowered by adding conditioning agents such as SO3 and ammonia to the gas stream to form a conductive layer on the particle surface. In coal combustion, SO3 produced from the oxidation of sulfur in the fuel acts as a conditioning agent. When the gas stream is above about 350 degrees Fahrenheit, increasing the temperature lowers particle resistivity. The collection plates, discharge electrodes, and gas distribution plates are cleaned by separate groups of components referred to as wrappers. Some wrappers provide the cleaning energy by mechanical impact, while others use vibrations. There are two basic types of wrappers, roof-mounted and side-mounted. With roof-mounted wrapper designs, there are a large number of individual wrappers, each connected to a single discharge electrode support frame, a single gas distribution plate, or a section of collection plates. For collection plate and gas distribution plate wrappers, the striking energy is transmitted down a metallic rod. For discharge electrode wrappers, the energy must be transmitted through an insulator rod to prevent carrying high voltage to the wrapper and the accessible areas on the precipitator roof. A side-mounted wrapper system has motors on the exterior of the precipitator that turn shafts that run across the interior of the unit. A set of hammers is mounted to these rotating shafts in order to wrap each individual collection plate and discharge electrode frame. For both types of wrapper designs, the frequency and intensity of wrapping must be carefully controlled in order to achieve proper precipitator removal efficiency. A wet negative corona ESP is useful for industrial applications where liquid particles must be controlled or where solid particles have undesirable electrical or physical properties, such as low resistivity or moderate stickiness. To avoid drying of the collecting surfaces, these units are usually preceded by a quench chamber or section to saturate the gas stream. There are two principal designs for wet negative corona ESPs: downward flow and horizontal flow. In downward flow units, the saturated gas stream is distributed to a set of vertical tubes that extend to the bottom of the collector. Discharge electrodes mounted in the center of each tube charge the particles, which then migrate to the wet collection surfaces. Recirculated water moving down the interior surfaces of the tube carries the collected material to the sump. A horizontal flow unit uses alternating high voltage plates and grounded collection plates to form passages for the saturated gas stream. The high voltage plates have discharge electrode points extending from the leading edge of each plate. The negative coronas generated around these discharge points charge the particles, which then move to the wet collection plates. Cleaning of the collection plates is performed by a set of overhead sprays and by a set of sprays on a traversing header on the inlet side of each field. A mist eliminator is often used immediately after a wet negative corona ESP to remove entrained spray droplets and other particle-containing droplets that would otherwise be emitted to the atmosphere. Common types of mist eliminators used in wet ESPs include chevrons, tube banks, and baffle plates. Wet positive corona precipitators are used for the collection of organic mists from relatively small industrial applications. In these units, the discharge electrodes are separated from the grounded collection plates. Because of this, they are sometimes referred to as two-stage precipitators. The gas stream first enters the charging section, where positive discharge electrodes charge the mist particles positively. The charged particles then move through the collector section, where they are attracted to the grounded plates and then drain into the sump. The plates are manually cleaned on an intermittent frequency, depending on the stickiness and viscosity of the collected material. To review, the common types of electrostatic precipitators that capture air pollution are dry negative corona, wet negative corona, and wet positive corona. Components of ESPs include gas distribution plates, discharge electrodes, collection plates, wrappers. The capture efficiency a device has in collecting particles is controlled by various operating conditions that affect resistivity in ranges considered low, medium, or high. There are several factors that contribute to loss of performance in an electrostatic precipitator. These problems include changes in dust resistivity, resistivity conditioning system failure, excessive wrapping intensities or frequencies, wrapping system component failure, discharge electrode collection plate misalignment, discharge electrode failure, transformer rectifier or TR set failure, electrical insulator failure. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large electrostatic precipitators are well instrumented. However, smaller systems may have limited instrumentation. Because of the potential for electrical shock, portable instruments should never be used to make measurements of parameters not being monitored. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced control device efficiency. Visible emission observations and opacity monitoring data, if available, provide useful information for evaluating ESP performance. Slight shifts in average opacity indicate developing problems before the unit goes out of compliance. Puffing conditions observed at the stack and opacity spikes indicated by the opacity monitor also provide useful data. These may be associated with re-entrainment losses or the re-entry of particles into the gas stream during wrapping or with short-term increases in emissions from the source. By comparing the frequency of the spiking with wrapping cycles and process operations, it can be determined whether the problem is associated with the source or with the ESP. If the problem is with the ESP wrapping cycle, the data may be used to determine which field is responsible. Shifts in the resistivity of the material being collected may result in increased emissions. Resistivity changes may be evaluated from the electrical data for the precipitator. The most useful parameters are the voltage, current, and sparking rate for each field. When conditions shift from moderate to low resistivity, voltages in all fields decrease, currents in all fields increase, and the sparking rates in all fields decrease. When conditions shift from moderate to high resistivity, voltages in all fields decrease, currents in all fields decrease, and the sparking rates in all fields increase. Changes in electrical data that occur in a single field are indicative of an electrical or mechanical problem in that field. A significant decrease in voltage, together with an increase in current and an increase in sparking rate, may indicate a misalignment problem. Cycling of the voltage, current, and sparking rate can be caused by a broken discharge electrode that is swinging in the gas stream. If there is a decrease in voltage, together with an increase in current and a low or zero sparking rate, there is likely a short in the field. This may eventually result in the field tripping offline. A decrease in voltage, together with a decrease in current and an increase in sparking rate, may indicate a wrapper failure. A walk-around inspection of the unit is useful in identifying non-functioning wrappers. Since some wrappers operate infrequently, the operator should be asked to place the system in walk-around mode before conducting the inspection. In walk-around mode, the wrappers are activated sequentially, providing the inspector the opportunity to observe each one's operation. The wrapping intensities and frequencies should also be evaluated. These should be adjusted for the approximate resistivity conditions that exist in the unit. In general, wrapping frequency is highest in the inlet field and decreases toward the outlet field, which has the lowest wrapping frequency. If the resistivity is low, the dust is weakly held and can be easily dispersed into the gas stream by excessive intensity or frequency of wrapping. If the resistivity is high, relatively high intensity and frequent wrapping is needed. However, there are practical limits. Extremely severe wrapping can result in failure of the wrappers or misalignment of the collection plates. Air infiltration into the precipitator can cause frequent insulator failures and corrosion of metal parts because of acid or moisture condensation. One way to identify significant air infiltration is from the gas stream conditions immediately upstream and downstream of the ESP. Increases from the baseline range of temperature drops indicate the need to identify and repair infiltration sites. Likewise, increases in oxygen concentration across the precipitator can be used to identify increased air infiltration. It is also helpful to conduct a walk-around inspection to search for air infiltration sites. Component failure records are useful in identifying factors contributing to the failures. These records show the spatial distribution of failures. If dates of failure are also included, it is possible to determine if the rate of failure is changing or if there is a specific event associated with the process operating conditions that is responsible. In determining if an electrostatic precipitator is working efficiently, field personnel should observe, if possible, any visible emissions, opacity monitoring data, shifts in resistivity electrical data across the entire system, changes in electrical data for a single field, wrapper conditions, air infiltration. The inspector should always be aware of the air pollution source's need to be in compliance with applicable rules and to observe the source's records and the control device's physical condition. Electrostatic precipitator systems used for air pollution control have many safety considerations, including electrical shock and sometimes explosive hazards and hot surfaces. Field personnel should never enter the inside of an electrostatic precipitator device. This type of equipment has legally specified methods for confined space entry under OSHA Rule 29 CFR 1910.146. Further training and experience will be necessary to complete all field tasks safely.